I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the 2025 AP Physics 1 FRQs. This is the final question. This is question 4, the Qualitative Quantitative Translation. In this video, we're going to talk about the fourth and final question of the 2025 AP Physics 1 exam. This is FRQ number 4, the Qualitative Quantitative Translation. So in this question, we have a scenario where we have a swimmer holds a block from mass m at rest in a tank of fresh water with a density of rho 1, as shown in figure 1. And the block is released from rest and accelerates upward with an initial acceleration of a1. All friction forces can be considered negligible. Then in scenario 2, the swimmer holds the same block at rest in a tank of salt water with a density of rho 2, where rho 2 is bigger than rho 1, so the density of salt water is larger. The swimmer again releases the block from rest and the block accelerates upward with an initial acceleration of a2. All friction forces in that situation also considered negligible. So part A asks us to indicate whether a1 is greater than, less than, or equal to a2 by writing one of the following in our answer booklet of a1 is greater than a2, a1 is less than a2, or a1 is equal to a2. We want to justify our answer in terms of all forces exerted on the block in each scenario, and we want to use qualitative reasoning beyond referencing equations. So we can't use equations necessarily to manipulate. So what we're going to do is we have forces, so we're going to draw a free body diagram. So we draw a free body diagram, and we know that the force of gravity is going to be the same in both scenarios because it says it's the same block with the same mass, so m times g will be the same for both situations. And we know because it accelerates upward that the buoyant force is going to be larger than the gravitational force in both scenarios. But the question is, which buoyant force is greater in order to have the greater acceleration? So in the case of the salt water, we know that a2 is going to be greater than a1. So a1 is less than a2 is what we would write in our booklet. And the reason for that is because the gravitational force is the same in each of the situations because it's the same block. Now, the more dense the fluid, that means the greater the buoyant force. And the greater the buoyant force means that you have a bigger net force, which means that in situation 2, you're going to have a greater buoyant force because the density of the fluid is greater, thus a greater acceleration. So in part B, we want to consider the general case where a block of mass m and a volume of v is completely submerged in a fluid of density rho. So starting with Newton's second law, we want to derive an expression for the initial upward acceleration, a, of the block when the block is released from rest. We want to express our answers in terms of m, v, rho, and physical constants as appropriate. We want to begin our derivation with a fundamental physics principle. So since it's asking us for Newton's second law, let's bring our free body diagram back. And the fundamental physics principle or equation from our reference information sheet, well, it's going to be Newton's second law, that the net force is equal to mass times acceleration. So the net force side of the equation is going to be the bigger force, which is the buoyant force, minus the smaller force, which is the gravitational force of mg, and that's going to equal mass times acceleration. Now, we're allowed to use m and g in our final answer, but we can't use the buoyant force. So the buoyant force, we're going to look up the equation for the buoyant force on our formula sheet, and we're going to find that it's the density times the volume of the fluid displaced times g. Now, this is the volume of the fluid displaced, but because the block is completely submerged, the block's volume is the volume of water that is displaced in this situation. So now we have variables that we're allowed to use. We have rho, v, physical constant of g, and m. So we just need to rearrange this equation to solve for a, and we get an equation of a is equal to rho vg minus mg divided by the mass. So here's our expression for acceleration. Now, part C asks us to indicate whether the expression for the acceleration that we derived in part B is not consistent or is consistent with the claim in part A. And we're going to briefly justify our answer by referencing our derivation in part B. So a tip, it should always match parts A and B. So if you're not sure how to figure it out, maybe do part B first and then come back to part A to try to figure out how you can explain it qualitatively before you can use equations. So in part A, our claim was that A2 with the more dense salt water would have a greater acceleration because salt water is more dense. With the more density means that we have a greater buoyant force. So using our equation from part B, which was A equals rho Vg minus mg divided by m, it can be seen that the greater the density of the fluid means the greater the acceleration. So if you increase the density, rho increases, that means the numerator on the equation on the right side gets larger, which means that the acceleration is going to be larger as well. So the equation from part B shows the direct relationship between acceleration and density. So that shows that the more dense the fluid, the greater the acceleration for the same mass block. So this is free response question 4 on the AP Physics 1 2025 exam. I hope this was helpful, and I hope you have a great day and even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cavi Coaches, and follow me on Instagram and X at Cavi Coaches.